I would like to introduce our guest speaker for tonight, Mr. Harry Tournay. Mr. Tournay is a senior scientist at the Association of American Railroads Transportation Technology Center in Pueblo, Colorado, USA. Prior to commencing at TTCI in 2002, Harry was the chief engineer responsible for research and development and design at Spoonet, South Africa, in charge of approximately 180 staff, 2,000 kilometers of track, 140,000 vehicles, 5,000 locomotives, and signaling section. Just imagine. During his 29-year career at Spoonet, Harry specialized in bogey design, vehicle track, and wheel-rail interaction on heavy haul lines. I had the pleasure of meeting Harry for the first time in 1997 in South Africa with Stephen Marich, prior to the 6th International Heavy Haul Conference titled Strategies Beyond 2000. At TTCI, Harry has been a lead researcher on the Strategic Research Initiative, SRI program, funded by the Association of American Railroads, AAR. These research projects are formulated primarily to support the leading 6 North American railroads with an enviable annual budget of approximately $12 million US. As part of this SRI program, Harry has managed research projects covering various aspects, including wayside detectors, wagons, bogies, as well as wheel-rail interaction. Tonight, he will share with us some of his research experience, which spans over 44 years. In 2005, Harry was inducted to the International Heavy Haul Association Hall of Fame in an acknowledgement of his expertise and contribution to the industry. Please welcome Mr. Harry Tournay to deliver the 2015 Stephen Marich Lecture in Railway Engineering, Strategies to Counter Wheel and Rail Rolling Contact Fatigue in Heavy Haul Service. Harry.
Thank you, Ravi, and distinguished guests, and all who are interested in rail wheel interaction. My title of my paper, Strategies to Counter Rolling Contact Fatigue in Heavy Haul Service, is focused really on freight railroads in North America, and it addresses what we're trying to do above the rail to help both the wheel and the rail, although it needs an understanding of both the wheel and the rail and contact fatigue in order to do that. So without any further ado, I think I'll go forward and just give you an overview of the presentation. I'll give you a bit of an idea of the problem size in North America as far as rolling contact fatigue, or RCF, goes, and describe some of the issues and some of the degradation modes we observe. And then we'll be looking at research status at this stage, what we're doing to address what I now call steering traction-induced RCF in terms of bogey design, also wheel development. I'll just touch on top of rail friction control and a little bit on curve design, because we need to just keep a broader view of things, and then give you a bit of an idea of what we plan as a way forward, implementing the bogey that we have developed conceptually, as well as where we want to go in terms of rolling contact fatigue research. We haven't really touched it, and we've been messing with RCF for Steve? And where we're going in terms of maybe an anti-shelling wheel, and maybe the metallurgical community here will be interested in that. So, what is our problem size? basically, wheel costs in North America are of the order of 800 million US dollars. And of that, and here we reference this pie chart here, which is audited wheel replacements by damage code. Of that, tread defects are probably 60% of the problem size, and of this, at least 50% is associated with rolling contact fatigue, and results in what we call high-impact wheels. Wheels that go down the track going bang, 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 and which you have to then remove. We estimate that the total RCF-related wheel costs annually in the US is of just a little bit larger than 400 million. Wear is not a big deal. It's something that we would really wish that wheels would be removed for wear. Wear is predictable, somewhat, and what happens when the biggest wear mode that we get is what we term asymmetric wheel flange wear. The wheel loses its steering ability and then moves and against one rail in one direction and wears the flange. This is a general wear mode that we encounter in the States, and what I observed in my time in South Africa. Wheel removals are a big problem in the US. This is here we have the incidence of what we call high impact wheels. We have wheel impact detectors that are situated along the track, and if you encounter a wheel above 90 kips, 90,000 pounds on the rail, you need to look to change it out, and you're mandated to change it out if it's above 140,000 pounds. And these blue skyscrapers here show you the removals, and you can see that the removals are seasonal. They're related to the snowstorms that you encounter in North America, and but not that predictable. You don't know which wheel's going to give you the problem after which snowstorm. And then the blue skyscrapers are the 90 kip wheels, and then the red tips on these skyscrapers are the 140 kip wheels. And you can see here that if you look in detail at the 140 kip wheels, the same pattern, seasonal in every sense. If we're looking at the rail costs, annual grinding costs in North America are around about 100 million. And if we look at RCF-related rail costs and they're associated with replacement, totally, that's a replacement of 300 million and 100 million due to grinding. It's costing the industry also about 400 million. So our total problem size in North America relating to RCF is of the order of 800 million. What are the damage modes? Starting with the tread, and the wheel's the easiest one to identify, because unfortunately the grinding guys come along and grind the rails and remove the evidence before we have a good idea of that. We have identified three wheel damage modes. The first, as I mentioned, is I've termed tread scuffing, and it's associated with surface damage. What happens basically is that surface-initiated cracks form, We call them cracks. They're actually wear-related, and I will explain that a bit more. And they then develop into cracks that go beneath the surface of the wheel, and eventually bits and pieces of the wheel fall out and cause so-called high-impact wheels. There's a very closely related failure mode, which is tread shelling, associated with the Hertzian maximum shear stress beneath the surface of the wheel, and related to subsurface fatigue. And what happens there is that we get delamination of the wheel. This white square here shows the delaminated portion of this tread identified by ultrasonics. And what happens then is that the delaminated portion then breaks out also to form high-impact wheels. Incidentally, if it doesn't break out, it forms a vertical split rim, which is something that we'll talk to a little bit later. Then we have identified a further mode. It's not all that prevalent. I have termed that continuous spalling, and it's almost a skidding of the wheel. You can see that, well, what happens is that we get little cracks forming there. It's related to heating and quenching of the rails of the wheel surface to form martensite, and this rather brittle layer then starts breaking out, and it occurs under light car conditions, under empty wagon conditions more than under loaded conditions. It's currently classified as tread shells in the American jargon, and that's just because the damage looks a little bit like a shell, and is longer than 1 inch in one direction, although it's not very wide. So, as far as the rail goes, we start with something which we think is very much related to the scuffing that we see in wheels, and it generates these patterns on the rail. This is dye-penetrant of the rail, and then bits and pieces break out very similarly to the to what happens with the wheel. And then you've got shelling as well, related to scuffing, which this is a particularly bad section that we didn't grind, and this is typical of the damage. Fine. So let's start with what we're doing about things, and we'll start with the scuffing damage, which we are addressing primarily by looking at improved bogey designs. And before we start off, I want to define something which is what we call the traction ratio, which is the ratio of the net vector sum of the creep forces between the wheel and the rail divided by the normal force. You can think of it as a demand for adhesion. It is not the coefficient of friction. And I'll refer to it in this talk as T/N traction ratio, so we know what we're talking about. And if we start looking at the damage that occurs on the wheels, we find that it occurs in 2 bands on the wheel, a primary band here and a secondary band here. And we've collected evidence as to the relationship between damage and the steering tractions. And this is a scatter plot of the measured steering tractions using an instrumented wheel set. And you see that the highest steering tractions are associated with these 2 contact bands. So I'm just giving you a couple of evidences for the relationship with steering tractions. Next one is some data from a set of cars that ran in coal service, predominantly in one direction, 80% loaded. And I looked at the wheel removals, miles to removal against the number of wheels removed for high impact wheels. And you can see that axle 1, which is the lead axle in the vehicle, is experiencing a lot more removals than axle 3, which is the lead axle of the trailing bogey, which is the next one that's subject to the higher steering tractions, and axle 2 and 4, which just go along for the ride, as it were, would probably show almost nothing if they hadn't run 20% loaded in the other direction. So there's some more evidence of that relationship with steering tractions. And here we have the comparison of wheel removals over a period of time, 500,000 miles, of a traditional three-piece bogey and a bogey with a better steering performance. So you can see again that there's a direct relationship to steering tractions. We've also gone in and I've played around with experimentally, and I borrowed a rolling rig up in Canada and introduced steering tractions between the wheel and a set of rollers underneath the platform here, and plotted the relationship of the steering tractions to the angle of attack of the wheel set. That's the angle that the wheel set takes up on the track relative to the longitudinal centerline of the track. And you can see here that as we start getting up into high tractions of the order of 0.3, 0.4 demand for adhesion, you move from a typically burnished surface of the wheel to a surface which has develops a pitting on the tread surface. And these pits are not cracks. They are actual pits, erosion pits, in the surface of the wheel, associated, I do believe, with stick slip, sort of semi-micro corrugation under these high traction loads. And to understand this a little bit more, we've got to go and dig into the so-called creep theory, where we look at the relationship of the relative slip between the wheel and the rail and the traction that is imposed. And I've got a little bit of a video here, if it'll work, which gives you a little bit of an idea of what's happening. Because in the contact patch between the wheel and the rail, we see both adhesion and slip. And some people find it rather difficult to sort of visualize how you can get adhesion and slip simultaneously. And here we see the wheel rolling on the rail, and the wheel and the rail, elements of the wheel and the rail, come into contact in different states of the strain. And as they roll through the contact patch, the strain, relative strain between those two, between the wheel and the rail, increases and increases until slip occurs on the trailing edge of the contact patch. And if you start then looking at the, oops, why can't, I apologize. If you then look deep into the eyes of the contact patch, you will find that there's a normal pressure distribution over the contact patch. But if you look in the area of adhesion and slip, you can see that relatively high tractions occur in the contact patch, even with relatively low tractions. So you're getting limiting slip incrementally or specifically at certain places in the contact patch. And we've done a contact patch analysis of the stress state on the surface of the contact patch. And you'll see here that at this transition between the area of adhesion and the area of slip, we can generate von Mises stresses of the order of 180,000 psi. And for those of you, all of you who are metrified, that's pretty much close to UTS of the steel. So I'm thinking that what we're doing is we're ripping bits and pieces out of the wheel under these conditions, and that's initiating rolling contact fatigue. Typically, if you look at the UTS of steels and you look at them at room temperature and at elevated temperatures due to the braking of the wheel, you plot that against the curvature in degrees of the curve through which the vehicle is trying to steer. You find that we've plotted these surface stresses that are generated against the curvature, not against the creepage, and the stresses. You can see that we're reaching very high stresses beyond ultimate in 4, 5, 6, 7 degree curves, and that is when everything goes well. That's not when you're traveling at underbalanced speeds and so on. And I'll talk to that a little bit later. So what we think is happening, and we're wanting to pursue this, is that these very high stresses result in material being torn out of the surface, very much as I showed in that cross-section a couple of slides back. And it may be exacerbated by microcollocation, high temperatures, that sort of thing. And it then creates a void in the surface of the material. And that void allows the material to flow. And when it gets the material flowing, you can start initiating cracks. If you sit and try and conceive of cracks just appearing in the contact patch without a void, it's very difficult. But if you're thinking of a void, that is definitely an initiator. And then these cracks then are driven down to the maximum shear stress and break out of the surface. We believe that ice forming and being pressed into these voids accelerates the generation of cracks and the initiation of high impact wheels, as we observe in service. And so we're coming to the conclusion that maybe this damage mechanism is not a traditional fatigue problem. It's maybe a wear-related problem initially. And the damage that you can generate in the experiment on the rolling load machine, you can get that damage after 5,000 cycles. It's as early as that. And so the damage is also now statistically related, because the high load cycles on a particular spot on the wheel, they've got to occur repeatedly on the same spot as the wheel is rotating and as the dynamics of the wheel sees the track. They are associated with low rail contact and not with high rail contact. So you've got to relate the number of load cycles also to left and right hand curves. The vehicle is also either loaded or not loaded, and it's operating in a lead or a trail manner. And then, of course, you've got the incidence of curvature, which drops off very rapidly in North American conditions. So you've got to get all of these things coming together in order to generate these high impact wheels. What are we doing about it? We developed a design concept which is based on the three-piece bogey, which you use typically in freight operations. And the three-piece bogey has a lot of merits. It's rough, it's robust. Its particular design allows it to go over very uneven tracks, which you typically find out there, and it has the ability or the property of having the coil springs and the dampers in the system located only at 2 points in the bogey, and also where there's a lot of volume to accommodate the deflections and the volume required for very high heavy axle load conditions. So the disadvantages, though, is that the wheel set can take up an angle of attack, and when it does so, it slides laterally against the flange and continues to slide on the low rail, developing a lateral creep force, and this is this force that is starting to generate the damage that we talk about. The other thing that it does, which is undesirable, is that it has what we call a low warp restraint. That means that the two wheel sets can move laterally in opposite senses relative to each other, and that initiates certain instabilities and poor curving modes that we'll touch on a bit later. So what we did in our design was to introduce what we call an adapter pad on top of the adapter, and that allows the wheel sets to angle themselves somewhat radially in the curve and reduce the angle of attack and and reduce the creep forces between the wheel and the rail. It's not a radial truck. I worked for 20 years in the radial truck design, and the radial truck does a lot better than this particular bogey, but it's a lot more expensive, and costs and benefits need to be considered. But as soon as you relieve the longitudinal constraint of the adapter pad on the wheel set, you set up the ability of the wheels to start hunting. It's a lateral instability of the wheel set on the track, and in order to avoid that, we have introduced then in the design concept either frame braces or a spring plank which holds the two wheels laterally in a lot more stiffer mode, and in doing so enables stability of the vehicle. In our jargon, it activates the lateral stiffness of the pad, and the lateral stiffness of the pad introduces reaction forces on the wheel set, which then stabilizes the wheel set. And here's examples of typical adapter pads. What we did is we produced the design concept and then went to the industry and said, please provide bogies according to this design principle. And so pretty much that's an established sort of pad that comes out of a particular supplier, and this is a new innovative pad that has been produced by a supplier, and these are examples of the shear stiffness, anti-warp stiffness that they have introduced to the bogey. Then the next thing is to say, well, okay, we've got these things. How do we evaluate a new bogey? And what we've done is we put together two loaded cars, one after the other, one with a standard three-piece truck underneath the vehicle, and the other with what we call the improved freight car truck, and we then compare them as we roll them around the track. And we've got this track out at TTC, which is what we call the wheel rail mechanism loop, and it has a number of different curves from 12-degree curve down to 3, and we precisely measure the steering tractions in the circular curves and then compare them, as I'll show you a little bit in the next slides. So here's typical results where I express the steering tractions in the form of distributions. This is the probability density of experiencing a particular traction, and there's the low rail traction ratio that I talked to, and you'll see that these are the tractions developed by a typical three-piece bogey in a 3-degree circular curve. This is a so-called M976, which is an improved truck which has been in service since 2004 in North America, and this is what we're proposing as the improved freight car truck. So that's what it looks like in a 3-degree curve. Of course, in a 3-degree curve, you don't generally develop high enough tractions to initiate damage. In a 4-degree curve, the tractions become somewhat higher, and in a 5-degree curve, they are in turn higher, and you can see damage starting on the 3-piece bogey. And then in a 7.5-degree curve, we still are able to maintain reasonably low tractions. In the tighter curves, 10 and 12-degree curve, we don't really get much improvement. But as I said earlier, this is not a radial bogey, it's self-steering bogey. This is a compromise for the American environment. And this is a summary of all these, all this data in terms of the degree of curvature against the traction ratio that's generated, and the blue is the plot of the medians of traction ratio for a 3-piece bogey. This is the so-called M976, and this is our improved freight car truck. So we get a much improved steering tractions between the wheel and the rail. This here is, I'm going to run through this very quickly, but this talks to the stability of the vehicle under empty conditions. The stability limit is shown in red on these graphs, and these are our measured stabilities. So basically, we have a vehicle that can curve properly, and that is stable under empty conditions. It's also stable under loaded conditions. And then we go into the rather obscure test regimes that we have in North America for pitch and bounce, twist and roll, where we excite the vehicle suspension at or near the resonance frequency. And because we have only friction damping, we have it's quite a tough test to pass. You can see it does pretty well here. There are issues in dynamic curving where we hit resonance at 15, 16 miles an hour, and we lose our vertical wheel load. We believe that this particular bogey can be modified to accommodate that. And this is typically the results of our twist and roll regime, where we excite the whole wagon body in twist and roll. So what our tests suggest is that if we allow some longitudinal stiffness at the axle boxes and at the adapters, and we somehow brace the bogey against lozenging or against warp, we activate the suspension laterally, and this allows the vehicle to be stable. We recommend, or we suggest, that you use these bracings. There's some suppliers who are still using the traditional wedge design, for those of you who are familiar with that, which sometimes works and sometimes doesn't. The wedges are in a stick-slip mode, and when they stick, the vehicle is stable. When they slip, you tend to get you tend to lose the warp stiffness between the bolster and the side frame of the bogey, and you introduce rather violent hunting, and you get almost a 10 times reduction in the warp stiffness of the bogey under those conditions, for those of you who might be dynamically interested. Hunting stability is still also a function of the rail and wheel profiles, and we recommend still that you address the gauge corner flange contact in a so-called conformal flange and rail, crown rail condition, pretty much as we recommended 15, 20 years back, rather than single point contact, which produces very high conicity, very high steering forces, cause the vehicle to be unstable, and results in very high contact stresses on the gauge corner of the rail. We also looked at the accuracy of alignment of the two wheel sets relative to each other, and using our so-called instrumented wheel sets. And you can see here that if you have radial misalignment of the bogey, you'll find that the vehicle, this is now curvature against the traction ratio developed. You'll see that it goes easier around one sense of curve and not around another, which is a reason also why often you get high impact wheels occurring on only one wheel of an axle and not on both. In terms of the warp stiffness, which is no, excuse me, this was a deliberately misaligned bogey with a particular misalignment. Here we are within particular limits of a 1/16th of an inch between a difference in wheelbase, and we find that the steering tractions are very similar, and probably that's about as accurate as you're going to get in a bogey out of just out of the shop, out of the foundry, out of being assembled, and that's typically the range of misalignments that we encounter in service. Here's a histogram of what we measure out in service. In terms of warp misalignment, because as soon as you constrain the two wheel sets laterally relative to each other, you've got to be careful of not introducing adverse steering conditions, pretty much like the wheel alignment on your car. And we found that within 3/8 of an inch that the two wheels are misaligned relative to each other. We don't get too much of a difference in forces from one curve to another, clockwise to counterclockwise. So we think that at this stage we've got a bogey which is capable of being rather friendly to the wheel and to the rail, but we don't put all our eggs in one basket. We're also looking at improved wheel steels beyond the so-called C-class that is prevalent in North America. And we are referencing now the Class D, and we had wheel suppliers produce the Class D wheel to the new specification, and we then tested these wheels in service, and you'll get a bit of an idea of the difference in performance. Here is a very limited test of a number of wheel sets placed in service. I won't go through the gory details, but basically we've done 250,000 miles at this stage on these wheels. And we are looking at wheel removals as a percentage against the miles to removal, and we're looking at it in a log form associated with the Weibull approach to analyzing these failures. And if you use the Weibull analysis, the slope of the curve gives you an indication of the type of failure, whether it's whether there's infant mortality or whether there's a wear or fatigue mode kicking in. And the so-called scale factor gives you the miles to removal of the 63.2 percentile of removals. So how many miles to failure at 63.2% of removals. So that gives you a bit of an idea of viable. And if we plot viable for all our wheels, comparing C-Class C and the high-performance wheel, and we look at all removals, there's not much of a difference. There is a certain difference, but these are all removals. This is for bearings, for what we call owner removed. Sometimes the owner removes a wheel for various reasons known only to himself. So we took out all the other removals and looked at just high impact wheels, and this is the sort of improvement that we can get. We're looking at by improving the wheels, possibly at this stage improving the wheels, the miles to removal from 336 to 543. That's a big deal if you think of our cost of removals of 800 million. Interestingly enough, as I said, the steering tractions are the big deal as to the formation of high impact wheels. And here you see axles 1 and 4 separated out against axles 2 and 3 for C-Class wheels in a truck with a modicum of good steering. So we still haven't, just by that so-called M976 bogey that we put in, haven't really fully addressed the removal due to steering tractions, hence our so-called high or improved freight car truck bogey that we're looking at. However, if you look at the removals, this is for C-Class wheels, if you look at the removals for D-Class wheels, the jury's still out. Axles 1 and 4 and 2 and 3, in fact, axles 1 and 4 are doing better than 2 and 3 at this stage. So but there are very few removals at this stage. So let's just see how things pan out beyond 300,000 miles in service. So, as far as the high-performance wheel tests go, certainly they're still ongoing, and we plan further tests and introducing further wheels into service. As far as top-of-rail friction control, if we're looking at the demand for adhesion between the wheel and the rail, if you can put some form of friction control, reduce the tractions between the wheel and the rail, surely you can improve the rolling contact fatigue. And yes, there is an improvement. Here's an improvement wear related on the low rail of curves that we've measured, and on the high rail of curves, and there is a degree of improvement. But remember, you can't reduce the friction between the wheel and the rail too far, because of course the locomotives have still got to pull the trains. So there's only a certain limit to what you can do. Even with improving top-of-rail friction control, you can still see these traction-related damage that is occurring on the surface of the wheel and of the rail. Another aspect is super elevation. What do we do in curves? We bank the curves. We put in cant in order to introduce a force to counteract the centrifugal force that the vehicle experiences. However, that's okay if you're going at a particular speed, that design speed in a curve. But if you're not, you run into problems. Typically, this is a topic in North America where they want to use mixed passenger freight operations. And so you've got a track that's banked to accommodate high-speed passenger, and you come along with very heavy freight cars. And what do they do in these curves? And what they do is they start curving with a higher angle of attack in order to generate the creep forces necessary to counter the deficiency of the cant on the track. And here's measured forces laterally on the lead axle of a bogey due to cant cant deficiency. I won't go into it in detail. You can look at it at your leisure, but these forces can be quite appreciable. So what is our way forward? We've developed this integrated freight car truck design. We've evaluated 4 different bogey types, and we're going to first put them out on our so-called fast track facility for accelerated tests, where we run a 100-car train around in circles. This train doesn't have a driver or anything. It operates remotely, and this thing just goes round and round and round and round, and damages the track and damages the vehicles, and we get an idea of what's happening. So we're running those bogies at this stage at fast, and then we're also defining component load environment. We're introducing new components into the suspension system, so we better know about the load environment, and that load being also a heat and temperature environment. And then we will then develop performance-based durability tests and criteria. And we're conducting a cost-benefit analysis of this whole lot, and we're looking to monitoring these bogies in service. Just to give you an idea, out in the flat prairies of Pueblo, Colorado, this is the FAST facility where we operate our automated train. It's about 4.5 miles that this train goes around in circles. And that track, the so-called wheel rail mechanism track that I used to test the curving ability of the vehicles, is around here. It then completes a circle below the level of this photograph. In terms of rolling contact fatigue research, we've looked and we've talked a lot about the surface-induced tractions. I mentioned earlier about the subsurface induced tractions. We're developing we've built now a so-called rolling load machine, where we hold a complete full-scale wheel set in a test rig, and then we oscillate a piece of track backwards and forwards underneath this wheel, guiding it at various angles of attack. And Steve, what we do is the wheel here is a passive partner. The track presses up on the wheel just to prove a point. And so we're going into that business. We're looking at quantifying the maximum shear stress or the fatigue resistance of the wheel to maximum shear stress. Here you see under low tractions, you still get this subsurface stress. The high tractions only generate the stress on the surface of the wheel, and here's typical delamination that we're getting in wheels, and they cause a lot of trouble. If you let the delamination become too big and get it to approach the field side of the rail, then bits and pieces of the wheel, then bits and pieces of the wheel fall off and cause derailments and that sort of thing. What are we going to do about it? We're doing this, so we intend doing the fatigue, subsurface fatigue analysis under various temperatures of wheel, and here's the subsurface stress. This is the nominal from mesostress in the wheel at around about 130 plus thousand psi, and certainly it is of a concern to us that it's certainly occurring, this delamination in wheels, in a rather prevalent manner. The big deal with analyzing these stresses is that, of course, they're multi-axial in nature. So not only does an element of the wheel and the rail see a varying stress state, but the direction of the stresses also change. So we need to do rather sophisticated analysis in that direction. Also, of course, the wheel moves laterally on the rail, and so with a particularly new conical wheel on a rail, the number of cycles that this maximum shear stress sees at the center of the rail is quite high, because the motion that the element of the wheel sees is not that great. Whereas if you have a more hollow wear, maybe you get a higher, a longer fatigue life, because it's because an element of the wheel sees fewer cycles. This is the machine we've just built, where the track presses up on the wheel. We control the vertical load. We can simulate underbalance, overbalance conditions in curves, and the whole yellow part, the table, the track, is aligned at different, or is capable of being aligned at different angles of attack to simulate different curvatures. And so this is the latest toy. It's just arrived 2 weeks ago. And I'm busy trying to get the thing into service. And this is typically what it does. It's a bit like watching paint dry. So with that, Ravi, I'll conclude my presentation.